Well, welcome back. This is Unit 6.5. And although this is still thermochemistry, we're going to be talking specifically about heat transfer. Well, remember that heat is the exchange of thermal energy between a system and its surroundings. And energy always moves from higher temperature to lower temperature. And we're going to look at different ways that different materials absorb and release energy. First, let's talk about heat capacity. Not all materials absorb heat energy the same way. For example, this picture right here, back in the day, when I was growing up, we had a park in Weatherford where I grew up that we would go to called Cherry Park. And everybody liked to go to this park because it had a tall slide. And so it looks something like this, where you climb up this really tall ladder and then you slide down, and it was really fun. Now, the only problem with that was that it was made out of metal. And so during the summer, it got really, really super hot. Now, so hot that they had signs like this, that the playground equipment could be hot, because I remember one specific time during the summer, my cousin and I went to the park and she slid down, and it was so hot that it actually burned the back of her legs. She was in shorts and actually peeled the skin off the back of her legs. So that was really, really, really bad. And if you grew up, or your grandparents grew up in Texas or around this area, the oil derrick that's at Six Flags over Texas, that big oil derrick that they used to have this metal slide on it. And here's a picture of it right here. And you could climb up stairs like this up to the top of this slide, and you could slide down. Now, since they've since taken that away, they don't have that anymore, but maybe your grandparents would remember it. But if you'll notice, over this is an awning right here, so that the sun can't directly hit this because of that same problem. It was burning people. And so even though they had this cover on it, the metal would still get hot during the summer. So here's a close-up picture of what they would give you. They give you this canvas piece of material with a handle on it here, and you would lay the canvas down, and then you would sit on the canvas and hold this handle, and then they would push you to get you started to go down the slide. So ask your grandparents about it. They may remember that. But because of all of this, because metal absorbs heat a lot better than the composite material that playground equipment is used on nowadays. Like nowadays, they have this composite plastic material that they use, and it doesn't absorb heat as well. And so, I don't know, it's still kind of iffy on whether, in the middle of August, whether these are too hot to play on or slide down. But heat capacity is how much energy, and energy is measured in joules, that it would take to raise or lower the temperature of this material by 1 degree Celsius. So we can see that it doesn't take very much energy to raise metal by 1 degree Celsius, but it does take a lot more energy to raise it or lower it by 1 degree Celsius. And here you see from the movie A Christmas Story, where they dared the little boy to put his tongue on a flagpole, and his tongue actually got frozen to the flagpole. That's because not only does metal absorb energy, it also gives up energy, and this metal is much, much colder than its surroundings. All right, so specific heat capacity. So specific, that word specific is added to this because this is how much energy is required to raise 1 gram, specifically 1 gram of that substance by 1 degree Celsius. And so it takes a lot less energy to raise the temperature, say, of this iron bolt by 1 degree Celsius than it does an entire roller coaster that you may see at Disney World. Well, specifically, how much energy we're referring to is the specific heat capacity. And sometimes that's just shortened to specific heat. And here's a chart here of different materials, not only metals like you see here, but also alloys and other things like glass, ice, marble, and wood, and how they absorb heat differently. Now, the lower this number, okay, because this is a fraction, joules per gram, the lower this number, the better something absorbs heat. So when we look at cookware, the question is always asked, why do we have different kinds of cookware? Like this cookware is made of aluminum and this is made out of copper. Why would we have two sets of cookware? Well, because look at the specific heat. For aluminum, right here, 0.900. Now let's compare that to copper, 0.387. So you see here, copper has a better capacity to absorb heat. So you don't have to use as much heat to heat up copper, thus heating up your food, than you do aluminum. So copper is a preferred cookware. And a lot of people do own copper pots and pans. But why would we choose aluminum over copper? Even though the specific heat capacity of aluminum is a lot different than that of copper. Like it's almost, 2.5 times different. Well, that's because aluminum is a lot cheaper than copper, a lot cheaper. So where we may be able to get a set of aluminum pans like this for say $50 or $60, and you get 1, 2, 3, 4, 5, 6 pieces of cookware. Here you have 3 pieces of cookware, and this probably $100 per pot. So this small 3-pot set may be $300 because copper is a lot more expensive than aluminum is. Now up here, well, let's look over here. What's going to be even better than copper? Copper is 0.387. Here's gold. Gold is 0.129. So gold is even better than copper. So here we see a gold pan. It's made out of 18 karat gold, and they really do make cookware out of 18 karat gold. Yeah, so if you have a lot of money to burn, then this may be the way you want to go because it's going to cook your food a lot better. Okay, but who has that kind of money to burn? Now, this is what's called a stock pot, because you see these 2 handles on it. It's something like this, a stock pot, where it's made, to make big quantities of soup or maybe chicken and dumplings, something like that. But I looked this up. And so for a small saucepan, and this is a saucepan right here with a handle, these are saucepans because they have handles on them. For a small saucepan, now we're talking maybe this size or maybe even smaller than this size, maybe this size. For a small saucepan, 18 karat gold, a single pan is, let me pull this over, $1,500 just for one single small saucepan. So that's out of reach for a lot of people, most people. So that's why, even though it is a better metal for cooking, it has a lower specific heat, you don't see that very often. Okay. You really actually don't see copper pots and pans used very often either because it is quite expensive. So most people have aluminum or stainless steel cookware in your house. All right. So remember, specific heat, that's the amount of energy used to raise 1 gram of a substance by 1 degree Celsius. So it's the heat per 1 gram, 1 degree Celsius, specific heat capacity or just specific heat. All right, so in this section where we're calculating the heat transfer, the amount of heat absorbed or released can be calculated using this formula here. Q is equal to MC sub P delta T. Okay, and so this this Q here is used as a heat quotient or just the amount of heat in joules. Okay, and we can't use H for heat there because H is Planck's constant and we don't want to get confused with that. So they use just a Q. M here is the mass in grams of the material, and you'll usually see this as a lowercase m like I have here instead of the uppercase m. And that's in grams because look at the unit of specific heat capacity. It's joules per gram degree Celsius. So if you're given in a problem the amount of moles, say for example, then you're going to have to convert that to the grams because specific heat capacities are in grams degree Celsius. Okay, and sometimes this is usually just shortened to C. Okay, they drop the P on that. So it's usually shortened to C. And then, of course, delta T, the change in the temperature, and this is measured in Celsius because this is in Celsius. Okay, so an example problem that you might see is calculate the heat that's required to change 50 grams of water from 25 degrees Celsius to its boiling point. Well, the boiling point of water is 100 degrees Celsius. So we're going to change this from 25 degrees Celsius to 100 degrees Celsius. And it's 50 grams of the water. Okay, so let's use Q is equal to the mass. So this is 50 grams of water times the specific heat of water. The specific heat of water is 4.18 joules per grams degrees Celsius. And this is specific heat is something that's going to be given to you for each problem. Now, because water is used a lot, we remember that this is 4.18 joules per grams degrees Celsius. All right, and then the change in temperature, we see here we're going from 25 to 100, so that change is going to be 75 degrees Celsius, and we have grams here. All right, so you see that the units cancel, the Celsius cancels here, the grams cancels here, so we just have the unit of joules left, which is Q. All right, so 50 times 4.18 times 75. So it's just multiplying. So 50 times 4.18 times 75. I have my calculator. All right, so that's going to take 15,675 joules of energy. Okay, and a lot of times you'll see this as kilojoules. So when you get big numbers like this, sometimes it's changed over to kilojoules. Now remember, joules, if we want to change it to kilojoules, right? It's 1,000 joules per 1 kilojoule. So you're going to divide this number by 1,000. So you're going to get 15.675 kilojoules of energy instead of 15,000, that big number. All right, and so how many sig figs do we need? Well, this is 3, right? This is 3. The zeros at the end count because there's a decimal. So 3, 1, 2, 3. So we look at the 7 to see if a 7 rounds, and it does. So our final answer that we would report out would be 15.7 kilojoules of energy for that particular problem. All right. All right, so the heating curve. A heating curve, well, as you recall, from the beginning of the year, matter has 3 major phases, and that's solid, liquids, and gas. And what holds these in this phase is that the molecules are held together by attractive forces that are between the molecules. So they're called intermolecular forces. And when these molecules start absorbing energy, they start vibrating faster and moving faster until they can overcome this attraction that's between the molecules, holding them together in that phase. And so that's how they move from one phase to another. And each phase of matter absorbs energy in different amounts, and they have different specific heat capacities. For example, water, in the ice form, in the solid form of water, the specific heat capacity is 2.090 joules per gram degree Celsius. Okay, so ice absorbs heat better than water. And we know that because when we take ice and we put it in a glass or something, we notice that it starts melting right away and it melts really fast. But once it gets into the liquid form, it doesn't absorb very well. 4.18, that's a high number. So that's why when we put a pan of water on the stove to boil it, it takes forever to get that to boil. And if any of you have pools in your backyards, then you know that it usually is the middle of May, maybe around the 1st of June before the water heats up enough that we can actually comfortably get in the water and swim. Now, I know a lot of people spring break or jumping in the water, but that's a little too cold still. And then when it reaches the gas phase, it goes about the same heat capacity as ice. So steam heats up really well. Okay, so it's just the water phase where those attractive forces between the molecules are really strong. All right, now the same concept holds true for all substances, just not water. So there's a different heat capacity for a different substance. And for all of the problems that you're given, if you're given problems like this, they'll give you the heat capacities. And the heat of fusion or the heat of vaporization, it's called. So the heat of fusion and the heat of vaporization is the amount of heat that it takes to phase change. So here, like, let's start with this heating curve. This is a typical heating curve of any substance. Okay, so you have the solid form right here. So this specifically is water. And how do we know that? Because 0 degrees is where water melts from ice to liquid, right? Or ice melts, I should say. And up here at 100 degrees, this is where water liquid goes to the gas phase. So if we look at this graph, A, C, and E are the 3 phases of matter. So if we take water that's at negative 50 degrees, it's going to be a solid, it's going to be ice. And if we start heating that up and adding energy to it, like we put it in a beaker, right, and we start heating it up, it's going to stay a solid until it reaches 0 degrees. Because that heat that we're putting into the ice is being used by the ice to make its molecules start vibrating faster. Once it hits 0 degrees, see this flattens out here? That's because ice stops heating up. It's not heating up. The temperature of that is not heating up anymore because once it hits 0 degrees, the energy that we're putting into that is being used to break those intermolecular or to force some distance in between the molecules. The molecules are vibrating faster, so the energy is pushing them further apart. Enough so that it changes phases to liquids. So the temperature stops rising because that energy is not being used to increase the temperature. Now it's being used to put distance in between molecules. So once every piece, every molecule has a distance between it so that it changes from solid to liquid, then we're going to see the temperature start to rise again. And that's this segment right here. All right, so this is the liquid phase, and the temperature of that water is starting to rise and rise and rise until it hits this point. And when it hits this point, the temperature stops changing. Again, for the same reason, because that energy that we're putting in now is going to actually break the intermolecular bonds that are in the liquid so that these molecules can move freely as a gas. So this right here, this flat phase is when it's changing, phase changing from liquid to gas. And once every molecule has changed from liquid to gas right here, so it's all steam, then this segment E here is the gas or the steam that is heating up again. Okay, so this is what's called the heating curve of water. And every substance, like I said, has a heating curve that has 3 sloped areas and 2 flat areas. It just may be longer or shorter in different segments. All right, so here's a typical problem that you may see. It says calculate the heat that's required to change 50 grams of water at 25 degrees Celsius to steam at 120 degrees Celsius. Okay, so we have to look at the heating curve because we're going from 2 different phases here. We're going from liquid to steam. So again, here's liquid C, and it's at 25 degrees Celsius. So we're starting right here, and we're going up to 120 degrees. So that's going to be somewhere up above this 100, like maybe somewhere right here. So we have this segment that's sloped, this segment that's flat, and this segment that's sloped. That includes our temperature range. So what does that tell us? It tells us that we're going to have 3 different calculations because one calculation is going to be using the heat Q. Well, this is delta H, the heat of fusion, times the amount of water that we have. Now, fusion happens down here. This is the freezing point. It's called fusion. Okay. And up here, the heat of vaporization, that's when it's going from liquid to solid. Okay. So we need the heat of vaporization for this problem because we're going through this phase change. So here's the heat of vaporization. We're going to need this number, right? And we're going to need the specific heat capacity of liquid water and steam. Okay, so we're going to need the specific heat capacity right here of liquid and of the gas, which is steam. So in order to do this problem, let me clean this up a little bit. We're going to have three calculations. One calculation is going to be to heat the water from 25 to 100. One calculation is going to be to change it from a liquid to a gas. And the third calculation is going to be heating up the gas from 100 to 120. Okay, so we're going to have three Q's for this. Okay, one is going to be MC delta T because we use MC delta T to calculate the heat of a phase. So we have for this mass is 50, okay, times C for water. This is water, so it's going to be 4.18. And then I'm not putting my units in here, but this is grams. This is joules per grams degrees Celsius. And then the change in heat is going to be from 25 to 100. Okay, so that's 75 degrees Celsius. That's the change. All right, so again, C cancels C, grams cancels grams. You're left with joules. All right. And so we already calculated this, right? We did that on our previous problem right here. So it's the same. Okay. So we got, let's do it in joules, 15,675. Okay, so 15,675 joules. Okay. Now we're going to have to use this equation right here. So the heat of vaporization times the amount of water. All right. So lucky for us, the heat of vaporization that's given to us is in joules per gram. Sometimes this is given in joules per mole. So you have to make sure that the units match because here we're given grams of water. So if we're given the heat of vaporization in joules per mole, we're going to have to change the 50 grams of water to moles so that moles can cancel and we just have joules. Okay, but this is good because this is given to us in joules per gram and we have grams of water so that when we multiply this out, 50, okay, so it's the amount, right? Here's the amount times the heat of vaporization. So the heat of vaporization is the amount of heat required to phase change, and it's given to us here as 2250. Okay, and this is grams. And this is joules per gram. Okay, so grams cancels and just leaves joules. Okay, all right, so we need 50 times. So grab your calculators. 50 times 2250. Okay, that's 112,500 joules. Okay, and then now for our third calculation, we're going to have to calculate this segment, okay, from 100 degrees up to 120. So again, it's 50 grams times the specific heat of gas, of steam. So this is going to be 2.010. Okay, and this is joules per grams degrees Celsius. Okay, joules per grams degrees Celsius times the temperature change. Well, now it's at 100 degrees. So we go from 100 to 120, right? 120 right here. Okay, so that's a change of 20 degrees Celsius. Celsius cancels, grams cancels, leaving only joules. Okay, so grab your calculators again. 50 times 2.010 times 20. Okay, that's going to be 2010 joules. All right, so to get the total amount of heat, you're going to add those three up. Okay, so I have 15,675 plus 112,500 plus 2,010. So that's going to be 130. I'm just going to write it right here, 130,185. Okay, and that's joules. Okay, so if we were going to convert this to kilojoules, we'd move the decimal over 3 times. So we'd have 130.185 kilojoules. All right, so how many sig figs? 3 here, 4 here. We don't use conversion factors like these. We have 3 here, so we need 3, so 130. Okay, so the 1 tells us whether we round or not. So it's 130, but if I just put 130 kilojoules like this, that's 2 sig figs, and I have to have 3, so I'm going to have to put my point there. Okay, and I cannot add another 0 because that would make 4 sig figs. So 130 point kilojoules of energy. Or if you wanted to have this as scientific notation, we do 1.3230 sig figs times 10 to the second kilojoules. Okay, either one of these could be your official answer. All right. All right, so that's heating up a substance that includes a phase change. The law of conservation of energy. All right, so energy, remember, cannot be created or destroyed, only transferred. And because of this law, scientists can calculate the amount of potential energy that is in our foods. Okay, because here we see 4.184 kilojoules is equal to what's called kilocalorie. Now, this is going to be a good conversion for you, and I think it's on your reference materials. 1 kilocalorie, 1 kilo, 1,000 calorie is 1,000 calories. So take out the kilo. So 1 kilocalorie is 1,000 calories. And that's equal to 1 calorie. Look, now this is important. Capital C, lowercase c. There's a difference. Okay, 1,000 little c calories is equal to 1 capital C food calorie. Okay, so this is how the calories are reported on your food. See, it's a capital letter right here. Okay, and so when you look at nutritional facts that are on the side of products, you're going to see this C is always a capital letter C. Okay, because that is a food calorie, which is 1,000 lowercase calories, which is a kilocalorie. And this is all gotten using chemistry. So how do they calculate that? Well, they use what's called a bomb calorimeter, B-O-M-B, bomb calorimeter. And it's a device that has a beaker. Okay, so you start off with this beaker, and here is a crucible or an evaporating dish that has food in it, like 10 grams of food. Okay, they'll probably use 10 grams of food or 100 grams of the food because 110 have the zeros, and it's easy to calculate things with that. You just move the decimal. So they'll put an amount of food here, and then they have these 2 wires that come into this beaker. Now, this beaker is a sealed beaker, and it has an oxygen inlet here. So it has a way to deliver oxygen into this beaker. And this is sealed up, and it's submerged in another container that contains water. And it's totally submerged 100%. And within this water is a stirring rod, a stirring device, so that it circulates the water, okay, and a thermometer. Now, this container is in a third container, which is an insulated container, so that no heat can escape from this water to the outside surroundings. Because remember, heat is transferred from the system to its surroundings. So what we want to do is these wires that come in, oxygen is pumped into here because you have to have oxygen to burn. And this is pure oxygen now. And so things burn better in pure oxygen than they do in air, because the air, remember, is a mixture of carbon dioxide, argon, and oxygen. So pure oxygen is pumped in here so this can burn better. And these wires are electrically heated wires. So what happens is the food ignites in the presence of this oxygen and starts burning. And as this food combusts, remember combustion, it's an exothermic reaction, so it's releasing heat. And this heat is absorbed by this water. Okay? And it's the exact same amount of heat, because remember the law of conservation of energy says that heat cannot be created or destroyed, only transferred. So this heat from this food burning is transferred to this water, and this water absorbs the exact same amount of heat that this is giving off. So we have this thermometer here, so we take the temperature of the water and we can measure the change in the temperature of the water. Okay, and it's insulated here, so none of this heat is lost to the surroundings. It's all maintained within this water. Okay, and the stir, of course, keeps the water circulated so you don't get hot spots in the water. And so we use this concept of the law of conservation of energy to calculate exactly how much heat this food gave off when it was 100% totally, fully combusted. Okay, there's no food left. It doesn't burn anymore. Okay, and so this is the concept of the amount of heat that was lost by the food is going to equal exactly the same amount of heat that was absorbed by the water. Okay, so the heat lost by the food is equal to the heat absorbed by the water. So we have Q is equal to Q, because Q is heat, the heat capacity. All right, so what do we know is equal to Q? Well, we know that MC delta T is equal to Q. So here we have MC delta T is equal to Q as well. So if this is equal to Q and Q is equal to Q, then this MC delta T must be equal to this MC delta T. Now, here's the food. So if we know the mass of the food, right, and we know the heat capacity of the food and the change in temperature of the food, that's the same as the amount of water that we have, the mass of the water that's surrounding this. We know the specific heat of the water, and we know the change in temperature of the water, so we can calculate the Q, the amount of heat energy that's given off by this. So that's how they get your calories that are in food. And this same concept now can be used to calculate other things. Like, for example, if 50 grams of water at 15 degrees Celsius is added to 40 grams of water at 85 degrees Celsius, what's the final temperature of the system? So we can calculate that. Now, this is just one system being added to another system. So it could be, here in this case, water added to water, but it could be anything. Like, you're going to see problems that may say, a girl's earring is dropped into her coffee. Okay, so the earring is going to absorb heat. The coffee is going to lose heat. What's going to be the final temperature of the coffee when this happens? Just things like that. This can also be used to identify metals. So if we don't know specifically what kind of metal something is made out of, then we can heat up the metal to a certain temperature, drop it into water, find out how much the change of energy is for the water, so we can use that to rearrange the equation to solve for C sub P. Okay, this is the specific heat of that metal. And then we can compare this to known charts like we saw back here, this here, and we can actually identify the type of metal or alloy that metal is if we don't know the type of metal. So this is used for a lot of different problems. So let's look at how we would work out this problem. All right, so we have this system of water, and let's call this the hot water, okay? And then we have another system of water that's called the cold water. Okay, so there's two systems that we're adding together. Okay, so what you have to do here is draw a little picture. Okay, and let's start over here with cold water. Okay, and then the hot water. What temperature is the water that's cold, the coldest water of this system? Okay, and that's going to be the 15 degrees Celsius. Okay, and the hottest is 85 degrees. So when we pour these two waters together, it's never going to go colder than the coldest water, right? And it's never going to be hotter. If we pour cold water into hot water, it doesn't make it hotter. It cools off the water, right? But the cold water is not going to get colder. It heats up that water. So we have this range here that the temperature of the water is going to be between the final temperature. So let's put TF there as the final temperature of the water. It's going to be somewhere in between these. We don't know where it is because the cold water here, we have 50 grams of it, but we only have 40 grams of the hot water. So we can't say it's going to be exactly in between because we have different amounts of water. Okay, so we can use this concept to calculate that. All right. All right, so let's take the mass of the cold water. We have 40 grams, hot water. We have 40 grams of the hot water. So here's the water, hot water and its temperature. So we have 40 grams of the hot water, okay? And the specific heat of water is 4.18 joules per grams degrees Celsius, okay? And then we have the temperature. Well, we don't know what the final temperature is, but we do know that it's going to be lower than 85 degrees. So if you're going to calculate the change in temperature, I'm just going to make something up here. Let's just say it's 50 degrees, right? The final temperature. So if we say we have something that is at 50 degrees and the final temperature of it is 85, how do we get the change of that? Well, we take our 85 degrees, right, and we subtract the final temperature, which is the 50 degrees, and we're going to see that that's a 35 degree change. Well, we're going to do the same thing here, but we don't know that it's 50. All we know is that it's T final. So to get this, it's going to be 85 minus T final. 85 minus T final to get our temperature change. Right? Okay, so that's going to be equal to, now here's the data for the cold water. How much cold water do we have? Well, we have 50 grams of cold water, right? And the specific heat of water is 4.18. And then we have the temperature of the water. All right, so it's kind of the same way. So how do we get the change? Well, we know, like, let's use the same example. If this was the final temperature of our water, to get the change, we're going to subtract the 15, right? And that's going to give us, what, 35 degree change? So we have to take 50 minus the 15. So now this is T final because we don't know that it's 50. I'm just guessing. So it's T final minus 15. So on this side of the equation, we're going to have T final minus 15. Now that's the key. This change in temperature is the key to getting this question right, putting these in the right spot. Because if I had 15 minus T final like we did over here, then that's going to change the sign of this 15. And when we do all this algebra, that's going to give us a wrong answer, right? So we have to make sure we get T final in the right spot. Here, right? And here. Here and here. So getting this T final in the right spot is the key. So that's why drawing this scale is so important. Okay, so now what's the only unknown that we have here? Well, the only unknown that we have here is our T final. So we can solve for this. Okay, so this is going to take a lot of algebra to do this. So let me go through this algebra real quick with you. So 40 times 4.18. Okay, so I'm multiplying this first. and I get 167.2 times 85 minus T final. Okay, and that's going to be equal to, now I'm just going to simplify this, 50 times 4.18. Okay, and that's going to give me 209. Okay, and that's going to be minus TF minus 15. Okay, so that's my first step, is to simplify this, multiply that out. Now I'm going to have, let's make this easier on us, and let's not, I want to do the eraser. Let's not use T final. Let's use a different variable. Let's substitute in X. I want to use X for that. So we're going to say X is equal to T final. Okay. So now I have to distribute this 167 out to both of these terms. Okay. So I'm going to have 167.2 times 85. That's going to give me 14,212. Okay. And then this times negative X is negative 167.2X. Okay. Now that's going to be equal to, all right, so here we have 209X. Okay, and then positive times negative is going to be a negative. So 209 times a negative 15, that's going to be negative 3135. Okay, so now we have that down to there. So now we need to get all of our X's on one side and all of our numbers on the other side. Okay, so what I'm going to do here is I want my X's to be on this side, the left-hand side, so it's X is equal to something. So I'm going to take this number here. Actually, no, I'm going to, because of the negative signs, I don't want to deal with a lot of negative numbers. So this is a bigger number here. I don't want to subtract a big number from a negative number already, because that's going to give me a big negative number. So I'm going to do this strategically. I'm going to take this and I'm going to add, okay, because it's negative, I'm going to add a 3135 to both sides. So it gets rid of it here. So 14,212 plus 3135. Okay, so that's going to give me 17,347. Okay, minus 167.2x is equal to 209x. Okay. All right, now this is negative. So in order to get rid of this on this side, I want to add it to this side. Okay. So if I add a 167.2x to this side, it gets rid of it here. So that's going to leave me 17,347 is equal to, all right, so 209 plus 167.2, that's going to be 376.2x. Okay, now to get rid of this so that we just have the x, I'm going to divide both sides by 376.2. Okay. So my 17,347 divided by 376.2, that's going to give me 46.111 is equal to x. All right. So remember, x is our final temperature. So our final temperature of this system is this number. Well, how many sig figs do we need? 3, 3, 3, 3. So it looks like 3. So it's 46.1 degrees Celsius. Okay. Now this can be used with anything. It doesn't have to be, like I said, 2 cups of water. It could be ice and water. It could be an earring and coffee. It could be any 2 systems. All right, so let's look at a different type of question. Here we have a different type of question because On this previous question here, we were looking at this system being added to this system and coming to a final temperature. Well, this question is not like that. This type of question, well, let's just read through it. Anthracene is a unique aromatic compound composed of 3 fused benzene rings. It's a component of coal tar and can be used to make several different dyes. A 5.12 gram sample of anthracene, which is C14H10, was burned in an iron, that's going to be important, iron bomb having a mass of 1896, and that's supposed to be grams. The bomb was immersed in 2.9 liters of water inside a calorimeter. The initial temperature of all parts of the system was 20.80 degrees Celsius, and the final temperature was 36.6 degrees Celsius. Calculate the molar heat of combustion of anthracene. Okay, so we're calculating a total heat of combustion. So this is going to be total heat. So we're going to get the heat of the bomb and the heat of the water, and we're going to add those together. We're not trying to find a total final temperature, okay? We're just taking, here's the heat of the bomb, here's the heat of the water, get a total heat of combustion. It says molar heat, which is moles, heat per mole. Molar heat, heat per mole, okay? All right, so the two parts of this system are the bomb and the water. And so we have to calculate Q for the bomb, okay, which is going to be MC sub P delta T, okay? And we're going to calculate the Q of the water. We're going to add those together to get the total heat, okay? All right, well, the mass of the bomb is 1896 grams, okay? And the specific heat, now I said iron was important, okay? So here it gave us the specific heat of the iron is 0.448, okay? And that's joules per grams degrees Celsius because the anthracene was heated in the bomb. So the anthracene, when it was heated and combusted, gave off its energy to the bomb, okay? And the bomb, say, absorbed the same amount of energy that the anthracene gave off. So that's why we're using the bomb here and not the anthracene, okay? And so the temperature, change in temperature, well, it says here that all of the beginning temperatures were this and the final temperature was this. So we just have to get the change in temperature. So 36.6 minus 20.8. So this is going to be a 15.8 degree temperature change. Okay, so 1896 times 0.448 times 15.8. It's going to give us, let's see, did I do that right? Let me do it one more time. 1896 times 0.448. Yeah, times 15.8. Okay. Oh, I hit a wrong button. Sorry. 1896 times 0.448 times 15.8. Okay. 13,420.6464. Okay. Now, remember, we don't round until we get our final answer. Okay, so here we have the mass of the water. Well, here it just gives us liters. So let's look at that real close. So 2.9, I know you're going to be tempted to just plug in a 2.9 liters, but remember it has to be the mass of the water. This is liters. So if we have 2.900 liters of water, one conversion factor that you have to remember is that 1 milliliter of water is equal to 1 gram. Water is 1 gram per milliliter. That's the density. 1 gram is equal to milliliters. So for water, it's easy to take the amount of milliliters, and that's going to be the amount of grams. So if we have liters here, if we look real close, how to change liters to milliliters, there's 1,000 milliliters in a liter. So this is really going to be 2,900 milliliters. And if it's 1 gram per milliliter, it's going to be 2,900 grams. Okay, so make sure you use the correct units in this. It's going to be real tempting. Oh, here's water, 2.9. Boom, get a wrong answer. All right, so 4.18 is the specific heat of water, and it's going to be times the same 15.8 degrees Celsius change in the temperature. Okay, so let's see if I can calculate it correctly, pushing all the correct buttons the first time. All right, so 2900 times 4.18 times 15.8. Okay, that's going to give us 191,000. That's a big number. 527.6. All right, so we need to add these two numbers together. So 13420.6464 plus 191527.6. Okay, and this is going to give us the answer in joules. Okay, in joules. So that's going to be 204,948.2464 joules. Okay, that's a lot. That's a big, huge number. Okay, so if we were going to change this to kilojoules, we'd have to divide by 1,000. How many sig figs do we need? 3, 4, 4, 4, 4, 3. Okay, so if we were going to change this would end up being 205 kilojoules of energy. Okay, and I know that's right because I wrote the answers right there just to make sure that I would match it. All right, so 205 kilojoules of energy. Now this is asking for the molar heat, or the heat per mole. Okay, so this is the heat. So we need to do moles. So how many moles of anthracene did we have? Well, we have, let me write it over here, 5.12 grams. We need to convert that to moles. So I'm going to put it over 1. I'm going to put grams here and moles here because I want to get rid of grams and change it to moles. So 1 mole of anthracene, we need to figure out the molar mass. So we have carbon, which we have 14 of those. Carbon is 12.01. And we have hydrogen, we have 10 of those, and that's 1.01. Okay, so that's going to be 10.10. So what's 14 times 12.01? That's going to be 168.14. So the whole molar mass is 178.24. So I'm going to put 178.24 here. Okay. All right. So that's 5.12 divided by 178.24. That's going to give me 0.028725342 moles. Okay, so it's kilojoules per mole. So now all I have to do is divide these two. So 205 divided by 0.02872531142. And I'm going to get 7,136. Okay, and we need 3 sig figs. Oh, wait a minute. You know what I did? I made a big boo-boo. Okay, it's not 205. That's not my final answer. Okay, so I need to substitute in this number here. So 204.9482464. kilojoules. Okay. Because this is not my final answer, so I don't want to round that yet. That may change it up just a little bit. Let's see if it does. 204.9482464. I mean, I got close to what I have written down there as the correct answer, but it was a little bit off. So I don't want to, I want to see if I'm going to get closer. All right, so 2872531142. Okay, so 7134.761. That's enough. I don't want to write all the calculator vomit down there. Okay, so we need 3 sig figs. 1, 2, 3. So this number tells us whether we round or not. Did I say 3 sig figs? Yeah, 3 sig figs. So does the 4 round the 3? It does not. So I have 713. Now we can't just drop this 4 off because remember, and I say this over and over and over and over, this 4 is in the ones place. We cannot drop that out because then it changes the number. We don't have the correct number of places on the left side of the decimal. So this 4 doesn't round the 3, but it is a placeholder 0. Okay, so we have to add that in there. Now that still gives us 3 sig figs, but it's this placeholder. Okay, so now we see that matches what we should get. And so what are the units? Kilojoules per mole. Say kilojoules per mole. Okay, so this is right here the molar heat, or the heat per mole of combustion of anthracene, 5.12 grams of anthracene. All right. Okay, so that's it for this. Make sure you slap that like button right across the face. Give me a thumbs up and leave me a comment.